All right, so Assalamu alaikum. I hope you've seen the website. Two lectures I'm going to upload, which are going to be the makeup, but they're not going to cover new material. They are basically going to cover some examples of the material that we've already seen. One of those lectures will also deal with the tight binding model applied to graphene. So we'll derive the dispersion relationship for graphene as well. And that will hopefully open up windows for many quantum materials and two-dimensional materials. And we'll take, of course, an approach that is not going to use the quantum field theory, which is an easier approach in some sense. Today, I would, however, like to continue our discussion on semiconductors and deal with the conductivity in semiconductors and see how the conductivity varies with temperature. In one of the earliest lectures in this course, I mentioned that temperature is a really important parameter in many condensed matter physics experiments. So you want to know what something really is, you vary the temperature and measure some properties. And one of the properties that is most commonly measured is conductivity or resistivity. So the temperature dependent resistivity provides some idea of the electronic structure of materials. And so if you synthesize a new material, invariably in most of those cases, you would subject that material to a conductivity measurement by some of the well-known, well-established techniques like four-probe conductivity, van der Pau measurements, etc. So it's really important to understand how semiconductors have their conductivities varying with temperature. And in fact, one of the hallmarks of semiconductors is generally considered to be the fact that you increase the temperature, the conductivity goes up, in complete contrast with what you see in metals or insulators. So if I were to plot for metals a graph of the temperature and the conductivity, let's plot the resistivity, because this is something that is readily measurable in an experiment. You measure resistances. So from resistances, you can infer resistivities by incorporating geometrical factors, etc. So for metals, you generally know that as the temperature goes up, the resistivity goes up. So how do you explain this? What's the naive explanation for this behavior in metals or insulators?
So that the atoms in the crystal start vibrating and they hinder the free movement of electrons as temperature is raised.
So they impede the free motion of electrons. So the atoms are vibrating and they present themselves as targets to the electrons. So the electrons now, when the atoms vibrate with a larger amplitude, the electrons have a larger cross-sectional area to collide with. So the scattering time goes down. They travel less distance in between scattering events. So their mean free length, path length goes down and the resistivity goes up. And at really low temperatures, temperatures that are less than a few kelvins, the resistivity just tapers off to some value rho naught, which is due to the impurities in the material. We also know we have other kinds of materials. For example, we might have a material whose resistivity suddenly drops to zero. And such a material is called a superconductor. And superconductors could be of different kinds as well, but at some critical temperature, the resistivity drops sharply, and it doesn't drop to some really minuscule value. It drops to big zero, real zero. And it's a quantum mechanical effect. So generally, one assumes that in semiconductors their hallmark, their signature property is that as the temperature goes up, the resistivity goes down, some kind of function like this. Now, today we're going to look at this in some closer detail, and we're going to invoke some of the concepts that we studied in statistical mechanics. So really, today we're going to do a statistical mechanical treatment of semiconductors. And then we're going to relate this with conductivity. All right. So would you like to ask any questions about our previous lecture about intrinsic and extrinsic semiconductors? Because we're going to use those concepts today. All right, so let's move on. Let's march on. So the band structure that I'm going to draw for our semiconductors is rather going to be a simplistic boxed version of the band diagrams. So I'm going to draw band structure simplistically in the following fashion. Excuse me, let me just get these cables out of the way. All right. So this is what I'm going to draw. So let's go a little bit further down. So I have a valence band and I have a conduction band, and they're separated by a band gap. The lower edge of the conduction band, let's call this energy EC, and the upper edge of the valence band, let's call it EV. And of course, this material exists at some temperature, so I have holes in the valence band, and I have some electrons in the conduction band. And my prediction is that I have a chemical potential right in the middle of the band gap. Now, this is an intrinsic semiconductor. I'm starting off my discussion with an intrinsic semiconductor in which the number density of holes and electrons is the same. So I have n electrons, and when I say electrons, I really mean free electrons in the conduction band. So this is just a shorthand way of saying something. Electron means an electron in the conduction band, and a hole means a hole in the valence band. So for an intrinsic semiconductor, the number density are n and p for electrons and holes, and n equals p. And this is how I define an intrinsic semiconductor. There's no dopant. And intuitively, the chemical potential lies right in the middle of the band gap. Okay, and I'm going to prove this later. All right, so now what I would like to do, I would like to find out n, and I would like to find out p from statistical mechanics. And in order to do that, I already know that if I would like to find out any number density, any number of electrons, I can integrate over the band, which means integrating over energy, and I would need the density of states, and I would need the probability of occupancy of a particular state, an occupancy factor. And since I'm talking of electrons here, this is the Fermi Dirac distribution. Okay, which is given by 1 over E raised to power energy minus the chemical potential K over KBT plus 1. And I can express this in shorthand as E raised to power beta E minus mu plus 1. All right. So I take the density of states, which tells us how those states are populated. And you've already seen numerous examples of how density of states are calculated. And you multiply each density of state with the probability of occupancy of that state, which is the Fermi Dirac distribution, and then you integrate. So if I would like to, I would now like to use this formula here. So, but before I use this formula, let's look at this problem from a graphical perspective. Now, if I were to plot the energy density, the density of states. So what does the density of states look like for an electron inside a three-dimensional material? Many states are available. The electron has to fill in those states. What does the density of states look like? Can you recall from one of our previous lectures? What's
like a Fermi sphere?
Yeah, the Fermi sphere is the volume in which states are occupied, but what about the density of states? Per unit energy, how many states would exist? They're equally spaced in K space, but what about the energy space? So it's going to be proportional to the square root of energy in 3 dimensions, right? If you recall. So here what we're talking about is that in the conduction band, the energies that I'm interested in, they are going to be proportional to, now the electrons only exist in the conduction band. So our datum for the energy should be the lower edge of the conduction band EC. So GCB should really be proportional to E minus EC square root with some constant of proportionality. And this constant of proportionality we've derived in one of our previous lectures is 2 mass of the electron raised to power 3 by 2 pi square h bar cube. Okay, and since we're talking about bands here, we have to replace this mass of an electron with the effective mass of the electron. All right, so in 3D, the density of states has, so if I were to plot this, E and JCB, that is the density of states in the conduction band, it tips off at EC and goes like a square root function. So this is valid for E greater than EC. All right. So look up your previous notes for this. Remember, in 2 dimensions, this becomes the density of states becomes a straight line. And in 1 dimension, it becomes 1 over under root 2. And in 0 dimension, quantum dots, it takes these spiky Dirac delta peaks. Okay, so this is something that you should take away from the condensed matter physics. For this is the most important, one of the most important facets of condensed matter physics. All right, so now what I would like to do is, if I were to plot GE, so if this is my energy axis, this is what the density of states looks like for the electrons. Likewise, for the holes, what I would have is a density of states that goes in the opposite direction like this. And this density of states will be proportional to EV minus E squared. All right. So, so electrons and holes, they live in the opposite realms. If in this diagram, I go higher up, for an electron, the energy goes up, and for a hole, the energy goes down. If in the same diagram, I go downwards, I descend. For an electron, the energy goes down, and for a hole, the energy goes up. In the conduction band, the electrons have a large number of levels available, and those levels have a density of states that is just akin, similar to an electron that exists inside a metal. Really, there is no distinction here. So we have multiple states that are available, whose density is given by the states that are available to an electron in a metal. The exact opposite relationship can be seen for holes. In holes, the conduction band is the landscape in which the holes can exist. And so the density of states also has a square root relationship. All right. So now what we would like to do is we would like to see what the Fermi-Dirac function looks like. So this is going to be a slightly cluttered diagram, but if on the same axis, I were to draw a Fermi-Dirac function at some finite temperature, this is my chemical potential. What will this look like for electrons? Remember that the Fermi-Dirac function is the probability that an electron exists at an energy E. Okay, so what does this function look like at some finite temperature? for electrons? Any clues? Any ideas? क्या इसको अगर प्लॉट करें तो कैसा होगा?
Sir, at first it should be close to specific value 1. उसके बाद वो slope down करके नीचे आएगा and then it will attain a constant value again.
It will become zero. It will become very
0.
close to zero. So it's like a unit step function. For energies below the chemical potential, it's almost 1. And for energies above the chemical potential, it's almost 0. But there is slight smoothing of the curve near the Fermi energy. So if this is my chemical potential here, for now I'm talking of electrons, for energies below the chemical potential, it's almost 0. For above the chemical potential, it's almost 0. For below, it's almost 1. This is 1 here. And then it just takes a turn like this, right? This is what the Fermi and Fermi Dirac potential, the occupancy factor looks like for electrons. Got it? If temperature were 0, which means that this B were infinity, then the curve would look like a straight hat function with square edges. But now we have some finite temperatures. Therefore, in this region of the order, for energies of the order of few kBTs, it deviates from this straightness, from this rectitude, and it becomes slightly curved. Okay. Now, if we were to draw the Fermi-Dirac distribution for the, so this equation is valid for holes and electrons. For holes, we will just replace this G with the G for the valence band and F for the holes. It's called FH. Here we have for the electrons, and this integral is over the valence band, whereas this integral is over the conduction band. So what will the Fermi-Dirac function look like for holes? Is it going to be exactly the same as the Fermi-Dirac function for electrons?
It should be a mirror image of it.
Shabash. It should really be a mirror image of it. So it's for holes, it should be 1 minus F of E. All right. Because a hole means really an absence of an electron. So you're finding the probability that the electron does not exist. That's 1 minus the probability that the electron exists. So it's really going to be a mirror image here. And if I were to draw this mirror image, the mirror image about the chemical potential, this is what it's going to look like. Okay, this is for holes. Now what I need to do, I need to multiply. For the electrons, I need to multiply this function with this red function. Okay, so the red function is making the product go to 0, but it's not really 0, close to the lower boundary of the band. It's still finite. Okay, so at some temperature, it is above 0 Kelvin, you might get a slight hump in the conduction band. And you might get a slight hump here at the top of the valence band. If the temperature goes further up, this curve slightly expands even further, but not much because of the exponential nature of the Fermi-Dirac distribution. In a sense, if you multiply the density of states with the Fermi-Dirac function, now I would like to plot something. Let me plot here. This is my energy. This is my chemical potential. This is my mu, this is my EC, this is my EV. What I'm going to get as a result of this multiplication is slight hump here, the slight hump here. So this is for the electrons. The area under this curve is the number density of electrons, and the area under this curve is the number density of holes. So electrons exist very close to EC in the conduction band, and holes exist very close to EV in the valence band. And you increase the temperature, this curve might expand a little bit. This curve would then expand also a little bit, so that the area under the two curves always remains the same. All right. So now we can also compute the number densities, and this will lead to an important facet. So let's compute. So is this clear? Can I proceed?
Yes sir,
ठीक है.
it's clear. Sir, लेकिन हम इन दोनों values को multiply क्यों कर रहे हैं? What are we
Okay.
going? What are we aiming for?
Why? Because we want to compute the number density, and we need to multiply GE with FE, right? So here there's a multiplication, right?
All right.
So if you want to find the total number of something, you look at how many states are available per unit area, which is the density of states, and what's the probability of occupancy of those states. And then you multiply the two, and then you integrate over the energies. That's how you get the total concentration of electrons per unit volume. Got it?
Yes sir, got it.
So we're going to derive some important results about semiconductors here. So if I would like to compute N, so N is A, the constant A, dE, and I need the density of state, which is E minus EC, FE, which is 1 over E P E minus mu plus 1. And I integrate from the lower edge of the conduction band to infinity. Now I use, you can evaluate this integral numerically, provided you knew what mu is going to be. For the time being, we only assume that the chemical potential is below EC, and it's many units of kBT away, which means the temperature is not very high, and this very high by the way means tens of thousands of kelvins. The chemical potential is inside the band gap, and it's so I'm assuming that EC minus mu, which is this gap, is much larger than kBT. All right. So the chemical potential is assumed to be away from the down under the edge of the conduction band by several kBT units. Okay. So this is my assumption in this calculation. And this is going to be true in most cases, by the way, unless there are conditions such as excessively high doping, etc. But if this condition is met, that is E minus mu is much larger than kBT, which is 1 over beta, then we can replace this integral. This is going to be much larger than 1. So I can ignore this one and take this into the numerator. And I'm going to be left with N equals A. All right, approximately. All right, now this looks like Does this look like some other occupancy factor, some other factor that you normally encounter in statistical mechanics? Does this ring a bell? This factor here. Doesn't this look like the Boltzmann factor? It does look like the Boltzmann factor, doesn't it? So you go higher up in the energy, further away from the chemical potential, the probability of occupancy decays exponentially. And this is what you see in a gas of electrons, which is being treated as a free gas of electrons. And this is exactly what is happening here. When these electrons go into the conduction band, large set of electron levels are available. The huge vistas, and most of them are empty, and there are very few electrons because the temperature is not really large. So very few of the electrons have the capacity to be promoted to the conduction band. In other words, they have the energy which is big enough to cross the band gap. They go into the conduction band, and now huge number of electrons are available. There is no concept of Pauli exclusion principle because the electrons can easily roam about in the entire space, and these electrons are now behaving like a free gas of electrons. Okay, and that's why we could also assume that the density of states was proportional to the square root as electrons inside, as we have electrons in free electrons inside a metal. Okay, anyway, so if I proceed onwards from here, I could do the following trick. I could replace this mu by EC, and then I would need to multiply with EC minus mu, I think, right? So this is my N. Okay, so this I've taken outside the integral because now this is a constant. Now I can replace this factor with some x. Let's call this x. This becomes dx. This EC becomes 0, infinity, x under root E minus beta x. Sorry, let's right. Is this making sense here? Okay, so let x square root be y. This means that 1 over 2 x minus 1 over 2 dx is y. This means that my dx is 2 x1 over 2 dy 2y dy. All right, so when I make this substitution, this becomes a e minus beta ec minus mu dy, y being multiplied with another y becomes y square, e minus beta x is now equal to y square. All right, so with these sleuths of hand, these substitutions, we can write this integral in a somewhat simplified fashion. Now, if you notice that this integral, this fraction here, this number here is really a derivative with respect to beta of e minus beta y squared. All right. This integral is a standard integral, and it gives, it's called the error integral, and its answer is 1 over 2 pi over beta. So far, so good. I'm left with a under root pi e beta. And this would give me 1 over 2 beta 3 by 2. All right, so now if I look at the expression of A, this is my A over here, this thing. I bring this down, put it back in here. I've done this at home several times. The answer that I would get is simply going to be equal to 1 over 4 2 me star kb t h square pi . All right, so let's take a half a minute break here while you assimilate this, and it's a simple integration. See you in 30 seconds. All right, so now this is factor here is a temperature dependent constant. You see, there's a temperature factor here. And there's also a temperature factor here in an exponent. So the variation of n will be more pronounced because of the exponential factor, because the exponentials vary faster as compared to polynomials or negative powers of t. So I can let's replace all of this with, let's call it nc e minus beta. All right, so I'm calling this factor nc. So what this really shows, this equation can be interpreted. And how can it be interpreted? It can be interpreted in the following way. I have an EC, a band H, and I have a chemical potential mu, even though there are no electrons at mu. Okay, no electrons at mu. It's inside the band gap, and it's an intrinsic semiconductor. There's no donor level or acceptor level so far. So EC minus mu is this gap here. And what the number of electrons that go into the conduction band. This equation can be interpreted thus that those number of electrons is going to be equal to some band gap EC minus mu, some energy difference EC minus mu, which is being exponentiated, of course, with a temperature factor. So electrons are getting into the EC level. The effective density of electrons in the EC level is NC, and the electrons that the probability that the electrons can jump into this NC level is given by this exponential factor E minus B EC minus mu. So whenever we have an exponential factor, it represents some kind of probability. And the probability factor has a power and an exponent which is given by the difference of the edge of the conduction band from the chemical potential. Higher this difference, because of the negative sign, smaller will be small n. All right. So this is how we interpret this relationship over here. All right. Any questions about this? This NC, by the way, is called the effective density of states at EC. So N, it can be interpreted as effectively how many states are available at NC multiplied by the probability of occupancy of that state. And the probability of occupancy of those states at EC is going to be given by how far above that band edge is from the chemical potential. And how big is the temperature, of course, because beta is 1 over kVt. Bigger the temperature, smaller will be N. Sorry, larger will be N. Larger will be N. And bigger this energy difference, EC minus mu, smaller will be N. All right. Likewise, if you were to repeat this calculation for the holes, exactly similar results would appear. Now you would have to do an integration from, so if you look at the band gap here, band diagram here, this is EV, this is EC. Now you're going from EV to infinity. So your P is going to be equal to sum A from EV to infinity minus, EV to minus infinity dE G in the valence band E F of holes of E. All right. So this is an integral that you need to calculate. This you already know. A E minus EV square root. This you know is 1 minus 1 over E beta E minus mu plus 1. All right. So you plug in these values and you can immediately derive a result which is analogous. So P is going to be NV, the effective density of states over here, into E minus beta. Now you're going to have mu minus EV. This is my mu. All right. So these two, you get two analogous results for the number density of electrons and for the number density of holes. All right. So now these are extremely important results. And we're going to talk about these results. So first of all, if I were to take N and if I were to multiply it with P, I will get NC, NV, E minus beta, EC minus mu, E minus beta, mu minus EV. The mu's will disappear and I'll get NC, NV, beta. This is simply the band gap, NP. All right. So let's backtrack a little bit and let's do some interpretation here. First of all, the number density of electrons, is it temperature dependent?
Yes, sir.
Yes, because of this factor beta here. Does it depend upon sorry?
NC can there be a temperature dependence here?
It's not pronounced. The more pronounced temperature dependence is in the exponential factor. Of course, it's in the NC as well. But the more pronounced temperature dependence is in the exponential factor, as it should be. Now, does it depend upon the chemical potential, the location of the chemical potential? Yes, it does, right? Because you have further up is the conduction band edge from the chemical potential, smaller will be n, right? So it does depend upon the chemical potential. Likewise, we can have the same argument for the holes. All right. Now, if I were to multiply n with p, this relationship here, does this depend upon the chemical potential?
No, sir.
No, it doesn't. But it's temperature dependence, of course. And it depends upon only on the temperature, the band gap, and possibly the effective masses of the holes and electrons, because Nc and Nv both contain, each of them contains respectively the effective mass of the electron and the holes. So it depends upon the band structure, but it does not at all depend upon the location of the chemical potential. What the chemical potential does is that it helps determine N and P. So these boxed relationships, or the relationships that I'm underlining in yellow, they work for any kind of semiconductor, be it intrinsic or extrinsic. If I were to put in n dopants inside this material to make an n-type material, so I get an extrinsic semiconductor, then there will be more electrons than holes, because the electrons are being contributed by the donors. So n is going to be greater than p. Excuse me. N is going to be greater than p, and n can be greater than p. Suppose for the time being that me star is the same as mh star. Let me suppose. So nc, the magnitudes of nc and nv are the same. So if n is greater than p, that is, I have n dopants like nitrogen inside the material, then, or arsenic or nitrogen, then what this implies is that n can be larger than p only if ec minus mu is greater than mu minus ev. Is that correct?
Yes, sir. Makes sense.
This means that if I get, so this is an intrinsic semiconductor, rough representation, 4 electrons, 4 holes, equal number of densities of holes and electrons. But if I put in more electrons in here, and those electrons are coming from some donor level, ed, then this chemical potential is going to shift slightly upwards. So mu n is going to be slightly higher than the chemical potential in the intrinsic case. So the chemical potential is a measure of the number density. If the number density of electrons and holes is exactly the same as in an intrinsic semiconductor, the chemical potential is bang in the middle, right in the middle. If you have more n-type majority carriers, then the chemical potential is shifted towards the conduction band. If you have more p-type charge carriers or holes, the chemical potential is shifted to downwards towards the valence band. Okay, so the chemical potential, one practical utility of the chemical potential is that it determines whether you have an n-type material or a p-type material, what kind of doping exists. But the product, so these relationships of n and p are valid for extrinsic as well as intrinsic semiconductors, only that the chemical potential has to be put in correctly. Now, if I were to multiply n with p, I will get a term that is independent of chemical potential. So this expression here is valid for both intrinsic and extrinsic semiconductors. It's independent of the chemical potential. Nevertheless, and it depends upon temperature, it depends on the band gap, and mh star and me star. All right. So this relationship here is called the law of mass action. And this is always constant. So if I put in more electrons inside a material and keep the temperature the same, then this product has to be constant. So if N goes up, P must go down. All right. So this is much like what we encounter in chemical reactions. So if I have a chemical reaction, A plus B goes into a product AB, then you know that you can define an equilibrium constant, Ka, which is equal to the product concentration divided by the reactant concentrations. So if A goes up, this goes up, this must also go up, right? So this is an equilibrium situation in which once the reactants on one side control the concentrations of the products on the other side. So now what we have in this semiconductor scenario is that electrons and holes, they are being generated in a thermal process. And they can also recombine, which means they can annihilate one another. So our effective semiconductor reaction is like this. Electrons and holes are being generated and they can also recombine. More electrons are generated. It means that more of those electrons will now recombine with holes. Because more electrons are available, then there will be, those electrons can also fall back and recombine with the holes. So the number of holes is also going to go down if there are more electrons. So you generate more recombination takes place. In fact, if you look at this relationship here, if you look at the right hand side of this relationship, and look at the left hand side of this relationship, the left hand side is really the rate of recombination. So the rate of recombination depends upon the concentration of holes and the concentration of electrons. More holes and more electrons, they will recombine more. Okay, just like a normal chemical reaction. If you increase this concentration, which is N, you increase this concentration, which is P, then what's going to happen is that the rate of recombination is also going to go up. Recombination happens whenever there is a hole and an electron. More electrons, more holes, the rate of recombination is higher. So the left hand side is really proportional to the rate of recombination. And what is the right hand side equal to? Can anyone guess? What is it effectively equal to? NC is the density of states at effective density of states at the conduction edge, and NV is the effective density of states at the valence edge. And you have a probability that an electron goes from the valence edge to the conduction edge, and that probability is given by this exponential factor. So the right hand side is really proportional to the rate of generation of electrons and holes. Right? Do you get this point?
Yes, sir.
So the law of mass action really is showing an equilibrium situation. And it is showing that the rate of recombination is proportional to NP is equal to the rate of generation purely by thermal means. NC and V probability gap. So the law of mass action is simply a statement of equilibrium, and it holds true for intrinsic as well as extrinsic semiconductors. All right. So Any questions about this? By the way, if we had an intrinsic semiconductor, that N is the same as P, let's call each one of them Ni. Then the law of mass action becomes Ni square is Nc Nv, and I can write Ni is, I can write this as Nc Nv minus beta Eg over 2. So I can find out the intrinsic semiconductors number of electrons. This is going to be equal to Pi, provided I know the band gap and the effective masses of the electrons in the holes. I can calculate how many electrons and how many holes exist at a certain temperature. By the way, the law of mass action holds an equilibrium situation, which means that there is no mechanism for deviation from equilibrium, such as external light illumination. The object is not connected to a battery, so that there is no potential difference, and so on. So can you this concept of chemical potential? There was a question in one of the earlier lectures about the chemical potential. So here the utility of the concept of chemical potential really comes to the fore. First of all, the chemical potential determines, and chemical potential determines P. So it determines the doping as well. Number two, if I were to take an electron from a semiconductor material, any semiconductor, intrinsic or extrinsic, and ionize it, which means I take the electron and make its potential go to 0, which means I strip out the electron from the semiconductor. Energy required for that process is called the work function. And that work function is excuse me. So that work function is determined by the chemical potential. Even though, it's really the energy, the chemical potential defines the energy that is required to take the electron out of the semiconductor material, even though no electron exists at the chemical potential because it's inside the band gap. All right. The third important thing is that, and this is really interesting. Suppose I have an N-type semiconductor material.
सर आपकी स्क्रीन शेयर नहीं हो रही, वो इनेबल कर देंगे प्लीज.
That's, I'm sorry. No, thank you. Suppose I have an N-type semiconductor material and I connect this with the battery. Okay, so there are electrons, free electrons inside this N-type semiconductor material. So it's N-type. And I connect it to a battery. So if this is my variable X, so I could plot the potential. So if I plot the potential, this you learn from your electricity and magnetism course, the potential is high here. It goes to 0 here. So it goes like this. So this is X naught. Okay. Right? Is that correct? So this is the electric potential. If on the same curve, I would like to plot the energy of the electrons, let's call it Ux. It's going to be given by E minus EVx. That's the potential energy of the electron. And let me plot this. This is what it's going to look like. Okay, so this is a plot of Ux, the potential energy of the electron. So the electron has a low potential energy here and it's a high potential energy here and a low potential energy here because this is negative, right? So it's highest here. So an electron would like to, a free electron inside this material, which is the majority carrier, would like to denote those majority charge carriers by field circles. They would like to move from the high potential energy to the low potential energy. They will be transported. Electron transport is going to take place. Right? So in the case of this electron transport, what we do see is that the average energy of the electrons is high here and low here. So if I were to draw the chemical potential of this system with respect to X with some arbitrary reference, the chemical potential is going to slope downwards. And this electron is going to move from, so now this axis is my chemical potential, this is my X. So its electron is going to flow downhill from a high chemical potential to a low chemical potential. Just as in if you have an electron and it is transported across the potential difference delta V, then this object is going to be equal to the work done on the electron. So the battery is doing work on the electron, and the amount of energy that the electron picks up as it is transported through potential difference delta V is going to be given by the charge on the electron into delta V. All right. So exactly in the same fashion, this delta V plays the role of a chemical potential. In fact, the electron, the work done on the electron in this case is equal to the change in the chemical potential as the electron goes from the right to the left of this n-type material. So the chemical potential is also telling us the work done on the electron. All right. And the nice thing is, since the number density depends upon how far is EC from mu, and the number density does not change along the length of this n-type material if it's connected to a battery. The number density, there's no point that the number density is going to change. All right. So otherwise we'll have a charge accumulation on one end, which is not allowed because we have a battery that is continuously supplying electrons. Since the number density is constant, it's uniform throughout the material. It means that if I have a sloping chemical potential, the bands must also slope. So if I were to draw the band structure for this material, my EC is going to slope and my EV is going to slope. All of this is now my valence band. And all of this is my conduction band. So the entire band diagram, when it's connected to a battery, it slopes. All right. So this is the concept of chemical potential. If now this is an out of an equilibrium situation, the entire material is not at the same chemical potential. That's why charge carriers are flowing from one end to the other. If it were a p-type semiconductor, the holes would have gone uphill on the chemical potential landscape. So this is a general rule. In the chemical potential landscape, electrons flow downhill. They go from higher chemical potential to lower chemical potential. And holes go uphill. They go from lower chemical potential to higher chemical potential. And by the way, uh, is this all making sense? I'm giving you a really intuitive picture of bands and how these bands bend in response to the application of electric fields or connections to voltage sources. And I'm giving an intuitive and a very easy to understand notion of the chemical potential as well. So any questions before I move on?
सर यहाँ पे इन दिस डायग्राम तो देर आर सम पॉइंट्स जहाँ पर हमारा जो म्यू है तो इट इज़ इक्वल टू आइदर ई वी और ई सी, तो
कैसे
इसमें क्या होगा?
कैसे So EV, this is EV, this is my mu, this is my, sorry, this is my EV, this is my EC. Mu is in the band gap. The band gap remains the same because the material structure hasn't changed. The difference of EC from mu and EV from mu remains the same. So everything is parallel, everything slopes together.
सर isn't all of it existing at the same time? तो सर इसमें अगर मैं
No.
देखूं कि अगर if I take the last point from the blue graph and the first point from the pink line, तो वो
This is
आपस
y,
में
this is x-axis. This is along the length of the solid,
ओ alright, सही
right?
ठीक है.
This is how the now the chemical potential is not uniform inside the solid. It's non-uniform. It's sloping, and that's why charge carriers can flow. That's why current can flow.
ठीक है, got it sir, thank you.
Right? Okay. So, and by the way, one more thing. What we could also do is we could determine the chemical potential. So, if I were to have an intrinsic semiconductor, so what I'm going to do now, I'm going to talk about the exact location of the chemical potential. So if I have an intrinsic semiconductor n equals p, and both of them equal to ni, so if I divide n with p, I get 1, and this would give me nc over nv exponent. So I have e minus beta, e c minus mu, e minus beta, mu minus ev. So 1 equals nc over nv ec plus ev minus 2 mu. And you also know that nc over nv so this kind of relationship here. Okay, so now if I take the log of both sides, I can make mu the subject of this equation, and I'll end up with the following. This you can do on your own. Please. All right. So if I have my EC and my EV for an intrinsic semiconductor, if I'm at 0 Kelvin, the second term just goes away. This is 0. So my chemical potential is bang in the middle. However, if my temperature is non-zero, then depending upon whether the effective mass of the electron is higher or the hole is higher, the chemical potential can go slightly up or down, but it remains very close to the middle of the band gap. All right. So for intrinsic semiconductors, we know that the chemical potential is now right in the middle of the band gap. And if the electron and the hole effective densities are the same, then it's also going to be in the middle, no matter what the temperature is, because then the log is going to be equal to 0. Okay, for silicon, germanium, MH is slightly higher than Me star. The holes have a higher effective mass. So in most cases, the chemical potential is shifted downwards, slightly downwards with temperature. If I have an N-type semiconductor, we already know that for this is for the intrinsic. For an N-type, the chemical potential goes slightly higher. And by the way, there are donor levels here, ED. For a P-type, the the chemical potential goes slightly below the intrinsic level. Okay, and remember, always remember, we have these acceptor levels here. All right, so now I'm going to come to the real topic of today's lecture, which is about conductivity. I haven't even started. So any questions? Please do homework number 8. It's going to be ungraded, but still I would encourage everyone to go through the questions. So now if I look at the conductivity, let's denote the conductivity by sigma, and I know that the conductivity is coming from the electrons. So I need the mobility of the electrons, need the number of electrons, and I need the charge on electron. So here I'm using this symbol for mobility, not for chemical potential. So I have the mobility of the electrons, but the conductivity can also happen because of the holes. So both of them are going to contribute. So in any material, if you have an intrinsic semiconductor, there are holes moving in one direction and electrons moving in the opposite direction, one going downhill in the Fermi landscape and the other going uphill in the Fermi landscape. So now if we really want to find out any conductivity, so for an N-type material, N could be larger than P, by the way. So all of the conductivity is primarily coming from the electrons. So we really need to find out how the concentration N changes with T. So we want to find out how conductivity changes with temperature. I need to find out how N changes with T, and I also need to find out how the mobility changes with T. So both of them have an important role to play in determining the overall conductivity of the semiconductor. All right, so now I would like to see how N changes with T. I'm going to focus my attention on N-type material for simplicity. I could also focus my attention on a P-type material. The results are going to be exactly analogous. So let me draw the band diagram first. So I have some donor levels, ED, at energy ED. I have some chemical potential mu N. This is my conduction band, this is my valence band. All right, so this is my band gap, EG. Okay, now I have an N-type semiconductor material and I put in ND dopant elements. This is the number of impurity atoms I put in. And each one of them is donating one electron, by the way. One electron, remember that. So it's a pentavalent impurity. And those extra electrons sit at an energy EG slightly below the edge of the conduction band. And this is, I mentioned in the previous lecture, 0.1. It's actually 0.03 electron volt. It's even smaller than 0.1. Right? It's of the order of 30 milli-electron volt. And the thermal temperature is 25 milli-electron volts, by the way. So now what's going to happen is that suppose I start off at 0 Kelvin. At 0 Kelvin, there are no thermally generated carriers. Nothing can go up from the conduction, from the valence band to the conduction band because the band gap is so large. 1 electron volt. Okay. And you're at 0 Kelvin, so there is no energy for the electrons to go up. In fact, all the donor levels are going to be occupied as well. Because the thermal energy is not even enough for the electrons to cross the barrier EC minus ED. Even this is larger than KBT because the temperature is 0 itself. All right. Now, if I were to increase the temperature slightly, these electrons might slide to jump off into the conduction band. And N, the number of charge carriers that end up in the conduction band, if you increase the temperature, we will use a rule of thumb again. It's going to be equal to the effective density of states here, which is NC, and the effective density of states at the donor level, which is ND, square root 1/2 E minus EC minus ED over over 2 kBT. Right? So this comes from the law of mass action. So if you look at the law of mass action, if you look at this relationship here, so what I'm doing, I'm looking at this relationship here, or rather I'm looking at yes, I'm looking at this relationship here. Okay, so now what I'm doing is I'm replacing NC, the effective density of states at the conduction band, and instead of NV, I now have ND, which is the effective density of states at the donor energy level. And in fact, since each donor level can occupy only one electron of either upspin or downspin, because it's a pentavalent impurity, I need to divide this D by 2 as well. So I have ND over 2 instead of ND. So this is an intuitive explanation of this 1/2 factor. It can also be rigorously proved, but I don't have the time for that. And then I take the square root because of just of dimensional reasons. Because if I didn't take the square, I get the square of the charge density. And I also, when I take the square root, I get a factor of 2 here. And the energy gap that I need to jump is EC minus ED. All right. So now as the temperature goes up, N goes up, 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 up. But still, the temperature is not large enough for this transition to take place. This transition is still forbidden, or the probability of it is extremely, extremely low. Now this process keeps on happening, keeps on happening, keeps on happening until all of the donor levels are ionized. This regime for at some temperature, T, let's call it TS. S stands for saturation. At some temperature, all of the donated electrons have now gone into the conduction band. So if I were to draw a band diagram at TS, all of the electrons have now been promoted to the conduction band. The number of electrons in beyond this TS remains fixed at ND. As many donor levels are available, so many electrons exist. Okay, because now still the temperature is not large enough for this transition to take place. All right, or very few of these electrons can be promoted. So N is really equal to ND plus some intrinsic carrier concentration, but this is very small, so this is roughly equal to ND. So now the second regime has kicked off, in which the T is greater than Ts, but still smaller than some other upper limit, which is Ti. This is called the extrinsic region. This is where the electrons that are contributing to conduction are all coming from the donor atoms. But their number remains fixed at Nd, roughly, it remains clamped at Nd. Okay, so in the saturation or ionization regime, electrons are jumping over a tiny gap, which is Ec minus Ed. Once all of the electrons have been ionized, they have gone into the conduction band, saturation has been achieved, and now the number of electrons contributing to conduction remains almost fixed. The temperature keeps on going up, but still not many electrons are available to be promoted from the valence band. So thermal generation of carriers does not take place. All the electrons are now coming from the donor atoms. And this is why this is called the extrinsic regime. And this is where you would like to operate the extrinsic semiconductor. All right. Then finally, beyond another limit, Ti, would the thermal generation start to kick in. And in that case, electrons can be promoted across Eg, and holes will be created here, and electrons will be created here, extra electrons. And in this regime, N is Nd plus Ni, and Ni overwhelms Nd now. So this is roughly Ni. Remember that Nd in real semiconductors, Nd is much smaller than Ni in any case. All right. So if you have a million silicon atoms, out of those million, probably 1 or 5 or 10 would be impurity atoms. So the ratios are really, really large. So impurity means a very small impurity, 1 parts in million perhaps, unless you have a compensation doped semiconductor or a heavily doped semiconductor, which also have their uses because they give you high speed devices. Anyway, in this regime, which is now called the intrinsic regime, this semiconductor starts behaving like an intrinsic semiconductor, in which N is roughly equal to Ni, and this is roughly equal to Pi because of the law of mass action. All right, but it's temperature dependent. The temperature goes up, more and more electrons are being promoted. And in this regime, of course, N is going to be given by Nc Nv exponent minus Eg over 2 kBt. Remember that in this regime, we have an Eg, whereas in the saturation regime, our energy was Ec minus Ed. So we have 3 regimes: an ionization regime, very low temperatures; an extrinsic regime, that's where you would like to operate an extrinsic and an N-type or a P-type semiconductor. So most extrinsic regimes span the room temperature regime. But if you really raise the temperature to much higher than room temperature, you enter the intrinsic regime, in which thermal runaway occurs. Thermal runaway occurs means thermal generation of carriers kicks in, and the object is now behaving like an intrinsic semiconductor, even though it wasn't meant to be treated in this fashion. So if I were to make a plot of, say, natural log of the carrier concentration with 1 over the temperature. This is a strange way of making this plot, but this is how it goes. So this is my low temperature regime. This is my high temperature regime. I get a curve of this kind. Here the slope is going to be EC minus ED over 2 kb. Here the slope is going to be with a minus sign, it's negative slope, minus EG over 2 kbt. So this slope is higher, high slope, sharper, steeper slope, gradual slope. And in between, the carrier concentration remains fixed at ND. This, therefore, is the ionization regime. The extrinsic regime, and this represents the intrinsic regime of the semiconductor. So now we have a fair idea of how the carrier concentration changes with temperature. But that's not enough. You need to know how the mobility changes with temperature. Now, so we are over time. So I'll start off the next lecture. The next 5 minutes I'll spend on how the mobility is going to change with temperature. But let's just finish it. Sorry, let's just finish this. Any questions? I'll just take 5 more minutes. Even though I'm finding it hard to speak, but let's finish this off. Any questions? So in the high temperature regime, we have a high temperature regime and a low temperature regime for the mobility as well. In the high temperature regime, what's happening is that the mobility, remember from the Drude's model, the mobility is given by E tau over M. Remember this formula for the mobility. Mobility is higher if the scattering time is longer. So we really need to find out the scattering time. How does the scattering time vary with temperature? In the high temperature regime, the scattering is limited by the ionic vibrations. Larger the temperature, higher will be the vibrations. The higher vibrations will present a bigger scattering amplitude for the electron, for the free electron, in this case the n-type carrier. All right. So now how do we look at the temperature? So if I have an electron moving at some speed v, then a distance time, in a time tau, it moves a distance v tau, sorry, tau is the mean lifetime of the electron or the scattering time of the electron. But then it meets an ion. And the ion is oscillating. So the ion presents a scattering cross section, let's call it S. And the scattering cross section is equal to pi a square, where a is an effective radius of the area in which the ion is moving around. So it presents a cross section, a target for the electron. Okay, and the electron strikes it. Okay. So now if I were to close this figure into a volume, a cylindrical volume, this volume is going to be equal to the distance v tau into S pi a square. All right. So this is the volume in which one scattering takes place. All right. So if I had S scatterers per unit volume, then the product of ns with this volume in which one scattering takes place is going to be equal to 1. So because this is one scattering event. All right. So this is the volume and this is the scatterers per volume. I multiplied it to, I get the number of scatterers, which is equal to 1, because this is how I've defined tau. It's the mean time between two successive collisions. So it's the mean time in which one scattering has taken place. All right. So if I look at this expression over here, this expression is going to give me, let me see, tau is going to be given by 1 over v pi a square ns. So this is the scattering time for an electron. Now, how does this depend upon temperature? Can anyone give me a clue on which of these factors depends upon temperature?
NS.
नहीं यार, scattering centers तो वही है ना. You're not changing the density of the solid. The number of scattering centers is fixed. It's not changing with temperature.
Speed would depend on the temperature.
Speed. How does the speed depend upon the temperature? Half mv square. It's like a free electron here, whose energy is given by half mv square, and this is proportional to 3 by 2 kbt, the equipartition of energy. Half kbt is associated with 1 degree of freedom. Now you have an electron moving in 3 dimensions. So 3 times half kbt is the average energy of an electron. All right. So V is going to be proportional to square root of T. Correct? So the speed of the electron is proportional to the square root of T. Any other factor that depends upon temperature in the denominator here. What about this A square? Does this depend upon the temperature? A is the average amplitude of oscillation of the scatterer, the ion. Will this change with temperature?
Yes, sir, it should.
It should change. And how will it change? What's the dependence?
It will increase with temperature.
How much increase? Yeah, proportionality बताओ ना.
Square के हिसाब से.
Yes.
Square root का इसमें होगा.
Energy. What is the energy of a harmonic oscillator? It's proportional to half m omega square a square. Right? The energy is proportional to the square of the amplitude of an oscillator. But the energy is also proportional to 3 by 2 kbt. So a square is proportional to t. So which means that tau is proportional to t 3 by 2, or is proportional to t raised to minus 3 by 2. So the mobility is proportional to t raised to minus 3 by 2 in the high temperature regime. Is that making sense? So it's not a simple linear dependence. Let's look at the other limit, the low temperature limit. In the low temperature limit, what happens is that the ions are not vibrating with the large enough amplitude. The ions are mostly immobile, or their amplitude of oscillation is really small. So the electrons will now be scattered predominantly by the presence of impurities. The impurities are going to scatter in principle. So you have more impurities, you have more scattering centers. Their sheer number is going to control the mobility. And you can do a rough calculation, a classical calculation in the following manner. You could look at your impurity ion say arsenic plus, and there is an electron cloud. So there's a nucleus and an electron outside it. So if an electron comes in with some kinetic energy, it's going to pass straight through. But it's possible that an electron comes in close contact with this ion and is scattered. All right. So if this scattering event takes place, which means that the electron is deflected from its original direction, and that is going to happen when it comes close enough to the ion, a scattering event takes place. So we have to find out the probability of an electron coming close enough to the atom, and that's going to happen. It's going to depend upon how many scatterers exist. If there are more scatterers jumbled up into the same region, more of these scattering events are going to take place. So the concentration of the ions is going to matter here. So if I define a critical radius RC, I know that the thermal energy is 32 kBT for the electron. This is the kinetic energy of the electron when it matches the roughly equal to the potential energy of the electron here. Then the electron is going to be deflected. If the kinetic energy is higher, which means the potential energy is smaller, the electron is going to be unscattered. So our scattering regime kicks in when the kinetic energy of the electron, the average kinetic energy, almost becomes roughly equal to the potential energy of the electron at a particular point. And the potential energy we know is going to be E square over 4 pi epsilon naught epsilon r, where epsilon r is the relative permittivity. And then I have an RC here. So I can solve this for RC. So if I if I were to solve this for RC, I would get proportionality 1 over T. Okay. But what I really need is now how does this RC depend upon S? So the scattering area is pi RC square, which is going to be proportional to my T raised to minus 1 minus 2. But my V thermal is also, the energy is also dependent on the speed. So this energy, this is proportional to, as I've already seen, T raised per 1 by 2. So I put everything together in my formula for tau, which is given here. Here is my formula for tau, this thing. So now what I'm doing, instead of pi a square, I'm looking at RC. Okay. And instead of NS, I have the impurity concentration. So I'm just changing how I'm calculating the scattering cross section. Instead of pi a square, I'm looking at RC. RC is the effective distance at which an electron will be scattered, distance from the nucleus. So if I put all these factors in together, I'll find out that my tau is proportional to T raised per 3 by 2. And sigma is going to be proportional to T raised per 3 by 2. So this is what I see in the low temperature regime. All right, ये बात समझ आई? In the low temperature regime, you use a different mechanism of calculating the effective cross section of collision. In the high temperature regime, this is given by the ionic oscillation. And in the low temperature regime, it is given by the effective distance of approach of an electron from the nucleus. All right. So far, so good. So the last thing is that if I were to plot on a log scale, the carrier concentration, this is what it's going to look like. This is 1 over T. This is low temperature, this is high temperature. And if I plot the mobilities in low temperature, I get T raised to power 3 by 2. I get a curve like this. And at high temperatures, I get a curve like this. When I multiply these two things together, my overall conductivity looks like this. In the extrinsic regime, it's predominantly determined by the mobility. Excuse me. Let me just make this clearer. When log n is constant, the mobility determines the temperature dependence. For high and low temperature, that is in the ionization regime, the charge carrier concentration determines the conductivity. In the intrinsic regime, the charge carrier concentration determines the temperature dependence mostly. Whereas in the extrinsic regime, which is the regime at which you would like to make an extrinsic semiconductor work, the mobility is determining the conductivity of the semiconductor because the charge carrier concentration remains almost constant. All right, so this finishes off my discussion of conductivity in semiconductors. In the next and the last lecture, I'm going to look at some devices, and the simplest device that I'm going to talk about is the Schottky device. I'm not going to talk about PN junctions or transistors because that's a huge field in its own right. I can't do justice to that in a single lecture. Probably a full course on semiconductor physics is required. I'll just see what happens when a metal makes contact with a semiconductor to make what is called a Schottky diode, and see how can we make solar cells out of Schottky diodes. All right, so inshallah, see you on Thursday. Thank you very much, and Khudafiz.
सर चैट में मरीम ने एक मैसेज किया है रिगार्डिंग द सिलेबस ऑफ फाइनल एग्जाम.
All right, so the next lecture on Thursday. Let me finish the recording just a moment, please.